Hey guys, what's going on? Today we're going to look at another interview question. This is Code That Up with Khan, and this question was asked by a bunch of big tech companies such as Amazon, Facebook, Uber, and probably many others. This is also on LeetCode, and it's a medium difficulty question. So let's get to it. Okay, so I have the question outlined here. It's actually, the question description is pretty easy. Given a binary tree with root and a target node, find all the nodes that are k distance away from the target node. So there's an image here. The root is 3, and our target node is 5. And the question wants us to find all the nodes that are k distance away, and in this example, the k is 2. So 7 is 2 steps away, 4 is 2 steps away from 5. And the difficult part of the question, I guess, is number 1. The node 1 is also 2 steps away because we can go back up to 3 and down to 1, so that's 2 steps. So this is kind of like treating the binary tree as a graph. So there are actually 2 solutions to it, and I use Swift, as you've probably noticed before, and the question gives us a class tree node, as shown here. So we have a basic node with left, right, and a value. However, the difficult part is, one way to solve this question is using a hash map. But in Swift, to use a hash map, your class has to conform to hashable protocol. And if it doesn't, you basically can't use a hash map on that structure. So this makes the question a bit more difficult to solve. However, there is another solution to it, which doesn't use hash maps or dictionaries. I've solved it both ways. So we're going to go with the non-hash map solution first. So I guess I'll explain the hash map solution, which uses, so basically for each node in the tree, we store their parents in a dictionary or a hash map, so that way we have access to the tree's parent, and that way we can go back up in our tree. That's solving it. So once we're on the root target node 5, we go back to its parent, and then we can try to get to node number 1 from that. So that's using hash maps. Without using hash maps is to traverse so search the left tree and then find all the k distance away nodes from it, but also search the right subtree, doing k minus the distance of 5 from the root to find all the other ones. So because 5 is 1 distance away from the root, and our k is 2, so we go 2 minus 1, and we find all the nodes in the right subtree that are 1 distance away. I hope that was somewhat clear. Here I'm just basically instantiating a bunch of tree nodes that are given to us using the structure, and once they're instantiated, they need to point to with the left-right values. So I basically build this tree the same tree that's shown in this example. And so basically in this one, I'm going to use 2 helper functions. The first function is a depth first search function, and then the second function is a subtree add function. And then this is the actual question asking to return an array of integers. So we're given a root, a target, and a k, which is our distance. And these helper functions are going to take out our answer array and modify it on the fly. So that's why inout is declared here. Okay, so I'm going to declare an answer array, which is going to be an integer. That's going to be initialized empty. Now we're going to run depth first search on this, and we're going to pass our root, targets, and k to it. K, sorry, and then our answer array. And we're going to Yeah. And then we're going to return our answer. Okay. So let me explain this depth first search function. So this is going to traverse the tree, incrementing a variable called distance, and going down the left and right path, of course. Each recursive call, we're going to increment our distance. So basically, if this depth first search function returns -1, it means no nodes are found to keep going in that direction, or otherwise we're going to keep going to iterate towards the distance we have. So we're going to check if our node is null. We're just going to return -1 here. We're going to check our base condition here. If r equals to the target dot value, we're going to add that to our subtree. So we're going to add node, 0 distance, k is going to be k, and our answer array. And then we're going to return 1 because we found 1. Otherwise, so this is the main part of the algorithm. We're going to define a left value. Yeah, this needs to be unwrapped. Left values, so we're going to call DFS with that. We're going to say node.left, target, k, and answer. I cannot type. We're going to define right value. We're going to do DFS on that, node.right. Pass our target, k, and answer. So once basically this helps us go down the left and the right paths of the tree. So here we're going to check if left is not -1, because remember this function returns, this is the recursive call, and it will return -1 if we're not going down. If we haven't found any nodes, it's going to return -1. So we're going to check if our left value is equal to k. That means we're on the target. So we're going to grab its value, and we're going to append that to our array. Node value. Then we're going to add that to our subtree, but we're going to add the right direction. Distance is going to be L plus 1, k is going to stay the same, answer is going to just get passed on. Then we're going to return L plus 1 because we want to increment our distance. So we're going to do the same for right hand side if r is not equal to -1. So we're going to check if r is at the k. If we're at the target, we're going to grab that. We're going to append that to our array. Then we're going to call our subtree add function with the left side of the node, and we're going to, otherwise we're just going to return -1. Yeah, so this is basically that. Am I missing something? Return. Oh yeah, we need to return here as well. Return r plus 1. Okay, and then our subtree add function is pretty simple actually. We're going to return our return nil if we don't have the node. If we're going to check if our distance is equal to k. Then we're going to append to our answer array. We're going to return append node.value. Otherwise, we're going to recursively also call node.left distance plus 1. K remains the same. Answer returns the same. Subtree add node.right distance plus 1. K and answer. So yeah, this is it. this is the whole algorithm. So I hope this makes sense. So because of this tree, 5 and K2, we should get 741 as our result. So if I run this distance K function, there it is, 741. Okay, so this is how to solve it on LeetCode using Swift. So the other way to solve it would be to actually, so I have it down here. Let me uncomment this so it's a little easier to read. So this is very similar. Nope, I copied the wrong function. Okay, here's the correct function. So basically, as soon as you start using hash tables, you see all these errors. Dictionary requires that tree node conform to hash table, of course, because you can't hash stuff without the object or the class conforming to it. So, and there are reasons why you may not want it to conform to hash table. For this problem, the LeetCode problem gave the tree node class without conforming to hashable. They just didn't make a change from Java to Swift or whatever language you're using. But because we're not in LeetCode, we can actually make it conform to hashable. So to do that, we need to do this as well as add a couple things to our class. So one is this function. If all the elements in the tree are known to be unique, we can just say return left-hand side dot value equals right-hand side dot value. If they're not equal, this is going to be false. There's one more thing we need to implement, which is hash. So this can be implemented this way. So this allows you to hash something in the memory. So we can just say we can combine the value and the left-hand side and the right-hand side. So this way our tree does conform to hashable. So these solutions would work too. I used value instead of val, I guess, in the way I solve this. And that's another way to solve this question. Both of these will be up on GitHub for you to take a look at. I hope this video is helpful to you. Thanks for watching.